we finish chapter 4, let's use this dashboard as production engineers rather than students following calculations. At the top, you'll see three boxes that summarize the entire gas lift process. The first determines PWF, the second determines the injection point, and the third determines the valve spacing sequence. Everything else on this dashboard supports those three engineering decisions. Now let's look at the design results panel. Immediately we can see injection depth, gas injection requirement, valve opening and closing pressure, number of unloading valves. This allows us to move from calculations to engineering interpretation much more quickly. Now let's start with a question. Looking at the pressure depth plot, where do you think the most important point on this graph is? Some people might say a static fluid level, some might say the point of balance, but from an operational perspective, the most important point is actually the red point, the injection point. Why? Because that's where gas enters the tubing and begins doing useful work. Now, let me ask you something. Suppose I reduce the valve differential pressure. What do you think happens to the injection point? Okay, so if I change this from left to left and right, what would happen? Will it move deeper or shallow? Take a second and think about it. When we reduce delta PV, the injection point moves closer to the point of balance. Okay, reduce and it moves to the point of balance. The dashboard immediately shows that change. This helps us visualize the concept that usually requires several manual calculations. Next question. If we increase the area ratio of the valve, what happens to the valve opening pressure? Higher, lower, or unchanged? Okay, so this is the area, and as you can see here, the plot of valve pressure versus area ratio. We have two curves here. Okay, so the valve opening pressure and we have closing pressure. So as you can see, by changing this area pressure, the closing pressure, by increasing the area ratio, the closing pressure reduced. Okay, so as a ratio, as the area ratio increases, the valve opening pressure decreases, making the valve easier to open, while the closing pressure remains relatively unchanged. Instead of memorizing equations, we can immediately see the relationship graphically. Now let's move to the tubing capacity chart. Imagine we're targeting a higher production rate. Can we just keep increasing production indefinitely? Of course not. At some point, the tubing becomes the limiting factor. This chart allows us to quickly check whether the selected tubing size can realistically handle the target production rate. And as you can see here, 2 inches is actually the right choice for our case. However, we also can change the choose 1.5 inches for our case. So next question, and of course this is my favorite part of the dashboard. Look at the optimization plot. Um, what happens if we keep injecting more and more gas? Do we keep producing more oil forever? Most of people, say yes. The graph says no. Initially, production rate, and we can, follow this from our technical or economic plot. So initially production increases because the fluid column becomes lighter, but eventually friction losses begin to dominate. The result is a peak. That peak is a technical optimum. So now here's the interesting one. If the technical optimum gives the higher, production, should we always operate there? Think about it. Not necessarily. Gas costs money. Compression costs money. That's why the dashboard also calculates the economic optimum. If the economic optimum produces 843 barrels per day, and the technical optimum produces 836 barrels per day, would you spend additional gas and compression power to gain only 2 extra barrels per day? Most students will say probably not. Congratulations! You are no longer thinking like a student. You are thinking like an asset engineer. In other words, the engineer who produces the most oil is not always the engineer who creates the most value. Now, look at the valve spacing table. Why do we need multiple unloading valves? Why not install only one operating valve? Because the valve must unload gradually. These unloading valves act like stepping stones, progressively moving the gas injection point deeper until the operating valve takes over. The dashboard lets us see the sequence instantly. So I give you another example. For example, the static reservoir pressure is 3000. Suppose that the pressure, static reservoir pressure decreases. So what will happen? So as you can see here, our injection point will move deeper because this needs to accommodate for actually lower pressure, and of course water and extra gravity needs to be actually a challenge here in our case. So before we finish, here's the challenge I would like you to think about. Could I predict that answer before moving the slider? If you can explain why the injection point changes, why the valve pressure changes, why the economic optimum differs from the technical optimum, and why the valve spacing looks like, the way it does, then you've understood the engineering. And that's the real purpose of this dashboard. The dashboard doesn't replace engineering judgment. It